Hi folks, we're going to take a look at number 10 from page 138. So we've got here a truck traveling at X kilometers per hour, and it's traveling between 30 and 120 kilometers per hour inclusive. Okay, and what R gives us here is the rate at which it uses gasoline in liters per 100 kilometers. Okay, and they give us the cost of fuel, 115 per liter, and they want to know what is the speed that's going to give us the lowest cost for a 200 kilometer trip, and they want to know what is that actual lowest cost. Okay, so here we're given a function, but what we have to do is determine a way to give the cost of this trip in terms of the speed at which you're traveling. Okay, so let's see how we can figure out doing that. So this here gives us the rate of fuel consumption per 100 kilometers. Okay, so liters per 100 kilometers, and excuse me, every liter costs $1.15. Okay, so we can take the rate, okay, in liters per 100 kilometer and just multiply that by 1.15 dollars per every liter. Okay, so that'll give us the cost per 100 kilometers. Okay, liters times cost per liter per 100 kilometers. But since our trip is 200 kilometers long, well, we know that it's going to be twice as much. Okay, so here we've got our cost function is just going to be, well, 2 times 1.15, so that's 2.3 times Rx is going to be our cost function. Okay, and again, we still have the same boundaries here. We're going from 30 to 120 kilometers inclusive. So what's nice about this is that if we're looking for a minimum cost, okay, all we have to do is work with the critical points and either of the endpoints, and whichever one of those gives us the lowest cost is going to be our answer. Okay, so let's go ahead now and do this. So 2.3 times C of X, so here, 2.3 times R of X, so let's multiply that. So we've got 2.3 out of 4 times 4,900 over X plus X. Okay, and so now we're going to optimize this function here. Okay, so let's take the derivative, C prime at X. Now, one thing I want you to notice here is this 2.3 ends up just being a constant times the function. So in the end, it's not going to affect the X value, which is going to give us the lowest cost. Okay, so we could have actually just worked with the function R at X to determine where our minimum occurs. Okay, but then of course in terms of actually determining the minimum cost itself, we would have had to figure out what we just did. Okay, but it's always nice to work with the actual function that we're optimizing. Okay, so let's take the derivative here. So the 2.3 out of 4 is just, 2.3 out of 4 is just a constant, so it doesn't affect anything. So let's take the derivative here. So it's 4,900 times x to the negative 1. So that's negative x to the negative 2. So this will just be negative 4,900 over x to the negative 2, so it becomes over x squared plus, and the derivative of x is just 1, so nice and easy. And we need to solve for when this thing is equal to 0, so that is when the bracket is equal to 0. So we've got 4,900 over x squared is equal to 1. Okay, and so 4,900 is equal to x squared, and x is equal to plus or minus the square root of 4,900. Okay, which happens to be very nice, so plus or minus 70. Okay, but here, since x lies between 30 and 120, and of course we're not interested in considering negative speeds, our only critical point is 70. Okay, now because we're working on a closed interval, I actually don't need to test whether this is a maximum, minimum, doesn't matter, because I'm going to need to test it compared to the two endpoints anyways. So what I have to do here now is I have to calculate C at 30, one endpoint. Okay, I have to calculate C at 70, which is my critical point, and I have to calculate C at 120, which is the other endpoint. Okay, so let's do this here. So let's go back to our function for C, which was given by this here. So let's start with 30. Okay, so we've got 2.3 divided by 4, okay, times whatever's in this bracket. So here we've got 4,900 divided by x, which in this case here is going to be 30, and then plus 30. So we get 111 and 17 cents. So 111.17. So that's our cost if we travel at 30 kilometers the whole way. Okay, and let's see how that compares to 70. So 2.3 divided by 4 times 4,900 divided by 70 plus 70. And here we got 80.5. So $80.50. So this is already lower. So now let's check at our other endpoint, 120. So here we've got 2.3 divided by 4. Okay, times 4,900 divided by 120 plus 120. Okay, and here we've got 92.48. Okay, so it turns out that this gives us our minimum. So now we can answer both questions. The speed at which we need to travel is 70 kilometers per hour. Okay, and so that's our speed. Okay, and our minimum cost traveling at this speed for the 200 kilometers is $80.50. Okay, so let's just do a quick recap here. Okay, so we were given a function for the rate of fuel consumption, but what we needed to optimize was the total cost for the 200 kilometer trip. So we had to figure out how to use this function and the other information given to determine a cost function. And then once we have the cost function, which is given over a closed interval, it was just a matter of finding the critical points and testing the cost function at the critical points and the two endpoints to find our optimal value. Okay, that's it.